Hello, my name is Hasini Balasuriya, and this is my presentation of the final report of the project for deep learning course. Um, so let me first brief you about the data pre-processing that I did for the RGB dataset first. So as you know, the classes were highly imbalanced. So I had to make sure that I make it relatively balanced. And in order to do that, I added some data for underrepresented classes from the internet available data sets. And for the extraction of image patches from those data, I used the highly trained, pre-trained end-to-end object detection model, which is DETR model with ResNet 50 backbone, um, to extract the image patches and then be saved in the particular classes. And then even if when those were not enough, I did the augmentation for those classes to increase the number of samples in those classes, which are not presenting a very considerable number compared to the rest of the classes. And for the majority classes, I did downsample them for a comparatively good number across the rest of the distribution. And after doing all this, I made sure I added them in such a way that it preserves the aspect ratio of the image and it's unique. It's equal for all the images, and all of them were resized to 64 by 64. Um, and the first analysis was done using CNN architectures, and I first did the baseline simple model for CNN using 3 convolution layers and 2 dense layers without any additional regularization. And I tested so many other combinations of hyperparameters such as learning rate, batch size, kernel size, and these different kinds of optimizers. And I found the best working combination of them to be 128 as the batch size, kernel or the filter size to be 3 by 3, and the learning rate was doing well at 0.001. Um, so this and the Adam optimizer was the one that I continued to use. So after keeping these stuff constant for the rest of the experiments, I increased the complexity slightly and observed with some regularization added on the way. And you can see the validation F1 score still did not yielded a huge difference between each trial, but the difference is in the curves. You can see the first trial to the last one, the generalizability has increased, and the curves are stabilizing really well and plateauing really well compared to the fluctuations that you can see in the first trial. So if you go to the confusion metrics, you can see that the models here, the CNN model is not doing a pretty good job in the predictions of classes across the distribution. You can see highly misclassified sets. So this definitely should be improved in the next models to go. The next one is the pre-trained model that we used. For this one, I used the VGG16 model. Um, in the first go, I did not train the backbone and I kept it frozen and only trained the classifier after extracting the features from the VGG16 model. But you can see the F1 scores were relatively really low. This immediately made me think of training the last block of the VGG16 backbone, and it yielded a good result straight away. So then immediately, eventually after that, I did train more layers, and finally I love the entire VGG16 backbone to be trained with the classifying or the dense layers. And this yielded a very good accuracy of almost 93%. And you can see finally, when I allowed all the layers of the VGG16 to be trained, it reached 94, almost approximately 94% in terms of the F1 score, validation F1 score. Even the scores here, the accuracy curves you can see is plateauing really well, stabilizing well, and it does not showcase any overfitting in the accuracy curves. So the confusion matrix, we can see that it has done pretty well compared to what we saw for the CNN model. And there are so many zero misclassified instances as well in this model. So moving on to the autoencoder. Um, First, I trained the autoencoder with different kinds of complexities. You can see on the RGB data analysis code, which I have shared with you. And ultimately, I reached a validation mean square error of 0.0026, which is really good. And I used the encoder part of it to on top of and build on some dense layers on top of it. And this yielded me with a 91% accuracy, which is the best I could do after experimenting so many different combinations of the architectures. But I can also observe some overfitting around the 20th epochs onwards. Um, Confusion metrics relatively similar to what we saw for the CN VGG16 model, and it has done good in many cases. But there are also a few highly misclassified instances, as this one, which the cars has been predicted as trucks. So, moving on to the final conclusion for the RGB models, the best model that I found from the experiments that I did for the RGB dataset is the pre-trained VGG16 model. And this again, while allowing the full VGG backbone to be trained along with the dense layers. And it yielded me a validation F1 score, which is the metric that I'm using to evaluate my models because of the imbalance that we saw for the dataset, even after balancing them out relatively better than what it was before. It yielded a 94% F1 score for the validation data. And even if there are some misclassified, highly misclassified groups, if we go back to the original samples, you can see some of these misclassifications can be justified because in cases like this, you can see the bike has been covered from something and this has been predicted as a car. Here, this light has been predicted as a sign because it's a black box that with no luminosity or no light appearing on it. So it's pretty much can be misclassified as a sign. So likewise, there are more examples that I have like visualized on the code itself. You can check out the last part of the code. Let me take you to the thermal image analysis quickly. So the pre-processing of this one is a bit different from what I did for the RGB dataset. The thermal data, I could not find good enough data from the internet for the thermal images. So what I did was I augment many of the underrepresented classes and downsample the majority classes. With that, I have a breakdown of classes as this, which is pretty good. So for the CNN model, I used two different architectures and one complex one simple one. And the one that worked well was the complex one where it had dropout layers for regularization and some complexity in the dense layers. It increased the F1 score from 89 to 93, which was a great improvement. And one mishap or one downhill that I saw in this model was the tension to overfit in the accuracy curves here. So, but the model is pretty well, doing pretty well compared to what we saw for the CNN model for RGB dataset. So it is a great improvement. And also, if we are generally comparing the two models, The CNN model for IR data has done well, more than what we saw for the RGB data. Um, Even if you go to the confusion matrix, the confusion matrix is improved really well from what we saw for the RGB dataset. And there are some zero misclassified instances as well, almost 5 zero misclassified instances, which is really good compared to what we had for RGB data. Uh, and for the pre-trained CNN networks, the first one I tried was the VGG16 model, but I expected a really good performance using VGG16, but I wasn't able to improve it much as I expected it to have. And then I used another much capable pre-trained model, which is ResNet 50 model, and it I experimented with it by freezing the backbone and slowly allowing last blocks to train. Eventually, I ended up training from the third block onwards, third convolution of block onwards, and I had the learning rate for this a lower number, and I also had so this was to avoid any large jumps in the gradient descent, of course. Um, and after having a considerably good performance, I also fine-tuned the dense model on top of it. Um, so after all this, the validation F1 score jumped from 90% to 96% finally when I trained 3 blocks of ResNet 50 model, which is a huge improvement. And the model you can see, uh, the training accuracy has almost reached 900%, while the F1 score follows, while the validation accuracy follows it of with almost 96% validation accuracy, and the F1 score is comparatively similar, and it's around 96%. And you can see the graphs are not overfitting and it's generalized well. And this is the confusion matrix, which is one of the best distributions of predictions so far across all models. And there are so many zero misclassified instances, and the misclassified instances of the highly misclassified instances that we saw where the cars were predicted as trucks were really low in this case. And you can see the rest of the distribution is also really good and not high in number. And I also checked the autoencoder models. Once again, that I used the encoder that I trained for the RGB dataset. And this case, I had a validation mean square error of 0.0010, which is really, really low. And I used this encoder on top of some and I built some dense layers on top of it, and different try different architectures of the dense models. Um, and after that, I was able to improve it up to around 90%, which is similar to what I reached for the RGB dataset as well. The graphs are looking okay and stable, and they do not show any overfitting cases. And the confusion matrix is relatively good, but not as best as what we saw for the ResNet model. So if I take you to some misclassified samples of the ResNet, ResNet pre-trained model, you can see some of these can be justified. Here in this sample, it should be predicted as a bike, but you can see 60%, almost 60% of the person can be seen in this image patch. So it's reasonable to predict as a person as well. And in this case, it should be predicted as a light, but you can see that it has captured as this, and it's a black box. So pretty much it could be um, classified as a sign as well. And in this case, maybe because the sign was captured at a distance and the shape of it is resembling uh, of a person, this has been predicted as a person. But there are some wrongly classified examples which cannot be justified like this and hard to be justified or explained either. But most of the misclassified samples can be justified like this, because the input data were not that great in terms of its resolution or the quality, and the sizes were really small. Even um, some of these patches that you can see over here are really, really small. And when they were resized to 64 by 64, the resolution changes, the clarity of the image has been lost. So this could be the negative impacts of using not so good data to train these models, but the models are doing fairly good, really, really good. So if I'm to analyze generally the RGB data and IR data classifications, IR images of buses and signs has been predicted better compared to the RGB images of them. And in contrast, motor RGB images has been predicted better than the IR images of them. But overall, the car class had the most number of samples in both IR and RGB cases, but these images has not been predicted so well by both the models. Maybe because I'm possibly thinking these could be misclassified with trucks and buses, given that if they were captured at a distance, this could be highly misclassified as trucks and buses as well. Um, so even though both of these models are capturing different like features, are being learned about different parts of a spectrum, which is infrared in one and the RGB data part in the other. Both the models are producing comparably good results and compatible results with each other, which is something great. And I hope the testing of my code will prove the same results that you saw on this report and work well. So let me take you to the code quickly. So for the testing of the data, I would like to take you to this part where you have to do this pre-processing that I have explained over here by setting up the paths for the pre-processing for your directory. And this could be the source. So this is the source path, and this is the target path. You can set it to be the same thing, um, or else you can name it as processed, test data processed or something similar to that. This does the padding and making it resized to 64 by 64 before inputting it to the testing process. Um, I have tested my model using 5 samples of each class, totaling it up to 40 test data images. And you can see the models have predicted really well. And I have carried out the confusion matrix and the classification reports as well. And this part I have done for the mapping that you had shared with us on the Blackboard. So I did not have time to retrain my models with the new mapping. So I did the remapping externally. So you can run this code to remap the classification over here to the new new class indices that you had shared on the Blackboard, and it will map back to the class indices that you had shared on the Blackboard, and it will give you the confusion matrix and the classification report as below. So this is for the testing. If I take you to the IR or thermal data analysis, this is my experiments, and these are different examples that I have tried to justify for the misclassification or else understand what is happening. So these examples are at the bottom of the page, and these are different parts. So each part has been divided using a markdown. And one thing that I have to mention here, pre-trained models have undergone process input or pre-processing different or specialized for the these pre-trained models, unlike the other cases where it was just done using manual or else I would say different different pre-processing compared to what we do for the VGG16. And for RGB data analysis, same process. I have prepped the data before and I have fed it, resizing them to a perfect size. And finally, you can see the misclassified samples once again. Um, and this is some extra work that I am showing you. This was the work that I have been doing for adding new data to the models. And this for thermal data preprocessing, augmented track, like adding new data. These were the work done before adding any data to the model. Um, yes, this pretty much sums up the explanation of my analysis for the project and also my codes. I hope the models perform as much as well as that I have explained on the report itself. Thank you very much.